This video is about the classification models using RapidMiner. Classification is the process of predicting the class of given data points. It is a task of approximating a mapping function f from input variables x to discrete output variables y. Classification belongs to the category of supervised learning where the targets also provided with the input data. Note that in classification modeling, you still have independent variables or input variables x, let's say x1, x2, up to x sub p, which predicts y. Unlike the linear regression where y is a numerical variable, in classification modeling, y this time is a categorical variable. It may be, let's say that your y is a classification of email, if it is a spam or not. Or in clinical settings is either that your y is the presence or absence of a disease. Or in marketing, let's say your y is whether a customer will purchase the product or not. How classification models work? Unlike in linear regression wherein we're trying to come up with a best fit line that predicts y, in classification modeling, we're trying to come up still with a line or any curve, but not to predict y, but rather to classify, to separate, or to group y. In this case, we have two groups of y. Let's say group A and group B. To show an example, suppose we have this data wherein, let's say, we have three independent variables or three input attributes. We have x1, let's say age, x2, let's say sex, and x sub 3, let's say this is white blood cell. And then your y, let's say, is the status whether a patient, let's say, have a leukemia or not. So 1 means the patient has leukemia, or 0, which means the patient doesn't have leukemia. So given this attribute, we have the true outcome of the patient. Now, the goal of classification model is to predict y. In this case, to predict whether a patient has leukemia or not. Now, how do we measure the performance of a classification model? Just like in linear regression wherein you have the actual value of y, in classification model, you have the actual classification of y, which in this case, let's say a patient has a disease or not. And what classifications model do is to predict y. In this case, still a categorical variable. Now, the accuracy of a classification model is whether it was able to predict the true outcome of y. In this case, the predicted outcome is present and the true outcome is present. So it's correct. In this case, the predicted outcome is absent and the true outcome is absent. It's also correct. However, take a look at this case wherein the predicted outcome is absent but the true outcome is present. Likewise, in this case, the predicted outcome is present and the actual outcome is absent. Through this, we may come up with the 2x2 table where it displays the true outcome or the true classification of y, let's say 1 and 0, or present and absent. And the predicted outcome still 1 and 0. Now, suppose this is A, B, C, and D. A here refers to the correctly predicted outcome, which is positive. D here refers to the correctly identified negative. And C here are the false positive and the false negative. So if we're going to have this 2x2 table, the measures of accuracy will be as follows. The accuracy, which refers to the correctly identified outcomes, either positive or negative, divided by the total, sensitivity, which refers to the percentage of correctly identified positive outcome among those with positive outcomes, specificity, which refers to the percentage of those who were correctly identified as negative outcome among those with negative outcomes, the true positive count, which refers to this value, which is A, and the true negative, which refers to this value, which is D. And last, we have the positive predictive value or the precision, which refers to the percentage of those who actually have the positive outcome among those who were identified as positive using the classification model. While negative predictive value, which refers to those who really have a negative outcome among those who were predicted of having a negative outcome. We also have the measures of errors. Accuracy refers to the correctly identified outcomes, while the classification error refers to the percentage of those who were incorrectly identified. And again, we have the false positive and the false negative counts. Then just like in the predictive analytics, Y will be classified if Y is present and if Y is missing. When Y is present, those data or examples will be part of the splitting process, wherein 80% will be used for the training and testing and 20% will be used for validation. When Y is missing, it will be part of the example dataset. And similarly, we want to have a model which has a better performance in the validation dataset as compared to the training and testing dataset. This is to ensure that once a new data comes in, the model has a better result as compared to the previous one. Now let's perform a classification technique using RapidMiner. We're going to open the file adsapproval.xlsx, which is a compiled dataset of 3 types of campaign materials dated from August 17 to 30, 2019. The attributes will be as follows: the day of the week, which is the day of the week when the ad was deployed, the campaign ID, which is the type of material, the age, which is the age bracket of the target user, and the gender, which is the sex of the target user. Consider here that the day of the week are expressed in categorical form. It's either Sunday, Monday, Tuesday, Wednesday, up to Saturday. Campaign ID, although this is numerical in form, this is the ID type of the material. Although age is naturally numerical, in this case, the age are expressed in brackets. Gender, which is either male or female. Note here that these attributes are categorical. Thus, there may be a need for dummy variables. The other attributes are numerical, which are the number of likes, the number of shares, the number of comments, the total impressions, the number of clicks, and the time in seconds spent of the user for the ads. Our dependent variable here is a categorical, which is either the product was bought or not by the user. Let's take a look at the file. Import the data adsapproval.xlsx. The attribute day of the week has no problem since it was classified as polynomial. The campaign, which is an ID, is supposed to be polynomial as well. However, it was categorized as integer. So we have to change its type to polynomial. Age has no problem as well since it was categorized as polynomial. Gender may either be binomial or polynomial. It's okay. The likes, the share, the comments, the impressions, the clicks are all categorized as either integer or real. So it was categorized as numerical. However, the dependent attribute, which is approved, was classified as integer since it was coded as 0 and 1. We have to convert it to categorical, in this case binomial, since there are only 2 possible outcomes, approved which is 1 or 0 which is not. Click Next, and Finish. First is, in the design view, drag the ads approval data to the canvas. Next, connect the out port to the results port. Next, we're going to make use of a sub-process operator by dragging it to the canvas. This will enable us to perform all the data preparation processes in that sub-process operator. Next, let's go inside the sub-process operator by double-clicking it. Once there, let's connect the in and output ports of the sub-process. This will enable us to continue all the operations preceding this sub-process operator and continue it with the other operators outside the sub-process. Next, we're going to use the set role operator. This will enable us to declare the approved attribute as our dependent variable. Next, choose the approved as attribute name and select label as the target role in the parameters tab. So this indicates that the approved attribute is our dependent attribute in the dataset. Next, for the categorical predictors, we're going to make use of the nominal to numerical operator. In the parameters tab, select subset in the attribute filter type. Select dummy coding in the coding type. And put a check on the use underscore in name. So this will enable us to perform dummy coding or to create dummy variables on the categorical predictors. Click Select Attributes. And we're going to declare some attributes which are categorical. In this case, we have the age, the campaign ID, the days of the week, and gender. Select those attributes, put it in the Select Attributes box, and then click Apply. Next, we're going to make use of the Select Attributes operator. In the Parameter tab, select Subset in the Attribute filter type. Then click Select Attributes. Select the following attributes such as Age ID, age 45 to 49, the last campaign ID 1178, the days of the week which is Wednesday, gender F, and reporting start in the selected attributes. This will enable us to remove these attributes eventually since they will be referred to as the reference attributes. Click Apply. Since they will serve as the reference attributes later, we have to remove them by putting check in the invert selection. Next, let's use the filter examples operator. And then in the parameter tab, select custom filters in the condition class. Click Add Filters and locate approved in the attributes and set it to is not missing. So what this operator will do is that it will separate those examples in which the approved status is present and whose approved status is not present or is missing. Once the approved status is present, it will be part of the splitting process. in which again 80% will be used for the testing and training, and 20% will be used for the validation. Those who are missing will be considered as in the example dataset. Click OK. Next, we're going to connect the unmatched port of the filter examples operator to the out port. So what we did in the sub-process are as follows. The setRole operator indicate that our dependent variable y is the attribute which is approved. This part created the dummy variables in which one of them served as a reference, that's why some of them were removed. The filter examples was used so that when y is not missing, it will be part of the splitting process in which 80% will be used for the testing and training and 20% will be used for the validation. However, if y is missing, it will be considered in the example dataset. Now let's go out of the sub-process operator by clicking the arrow up of the process. We're now going to split the data using the split data operator. Next, let's use the stratified sampling as the sampling type in the parameters tab. The local random seed would make sure that we will have the same split every time we run the data. Next, let's click Edit Enumeration. We're going to make use of the 80% and 20% ratio, so click Add Entry and put 0.8. Click Add Entry again and put 0.2. So this will declare again that 80% will be used for the testing and training, while 20% will be used for the validation. Let's click OK. For the setting of the optimization parameters, wherein this is used to find the best model on the criteria that can be made automatically out of the dataset. It gives the performance indicators as the parameter changes. Using the optimized parameters grid operator, in the parameters tab, choose fail on error in error handling, and double-click the optimized parameters grid operator to go in the sub-process. Next, using the cross-validation operator, connect the following: input port to example port, connect the model port to model port, the performance port to performance port, and the example and testing ports to the output port. Next, let's go inside the cross-validation operator by double-clicking it. So we now have the training canvas and the testing canvas. For demonstration purposes, we're going to make use of the decision tree algorithm as a classification model. So we're going to make use of the decision tree operator in the training canvas. Let's connect the training port and the training port of the operator. And connect the model port to the model port. For the testing operators, let's use the apply model operator in the testing canvas. Let's connect the model port to the model port. Connect the testing port to the unlabeled port. And using the performance for binomial classification operator, let's connect the label ports of the apply model operator and the label port of the performance operator. Connect the performance port to the performance port. Connect the example port to the testing port. We may check the manually set positive class and enter the value 1. This indicates that the approved attribute uses 1 as the positive outcome. For the measures of performance of the testing and training dataset, let's check the following: accuracy, precision, which is the positive predictive value, the sensitivity, the specificity, the true negative and the true positive, the classification error, and the false positive and false negative. Consider that these performance indicators are measures of accuracy, which indicates that the higher their values, the better. Whereas these performance indicators are measures of error, which indicates that the lower their values are, the better. Now let's go back to the optimized parameter grid sub-process. In the parameters tab of the cross-validation operator, click Edit Parameter Settings. Select cross-validation, then transfer the number of folds and sampling type in the selected parameter. Then click OK. For the evaluation of the model using the validation dataset, go back to Process. Using the Apply Model operator, connect the model ports from the optimized parameter grid and the apply model operators. Connect the parameter port of the split data operator and the unlabeled port of the apply model operator. Then let's use the performance binomial classification operator again. Connect its labeled port to the label port of the apply model operator. Connect the performance port of the performance to the results port. Again, this sub-process was used for the data preparation, wherein we were able to declare that the approved attribute is our dependent attribute. We were able to create dummy variables as well, in which one will be the reference, which will be deleted. And on our dependent attribute, which is approved, if the data are not missing, it will be part of the splitting up process, in which 80% will go to the testing and training dataset, and 20% will be used for the validation dataset. This operator is the one for the testing and training, which used 80% of our data, while this one, the model which was produced by the optimized parameter, using the 20% of the data, which is the validation dataset. Next, for the performance of the validation dataset, we're going to check the same measures such as accuracy, precision, which is the positive predictive value, sensitivity and specificity, true negative and true positive, classification error, and false positive, false negative. Again, note here that these are measures of accuracy in which indicates that the higher the value, the better. Whereas these are measures of error in which the lower the values, the better. Next, for the example dataset, we're going to predict the dependent variable y using the apply model operator. Connect the model ports of the apply model 2 and the apply model 3. Connect the output port of the sub-process operator to the unlabeled port of the apply model 3 operator. Next, connect the label and model ports of apply model 3 to the results port. Again, what we did are, on the sub-process, we were able to declare that the approved attribute is our dependent attribute. Some of the categorical predictors made use of dummy variables in which their reference was removed. And if y is missing, that will be part of the example dataset. And if y is not missing, it will be part of the splitting data process. Once the data are split into 80 and 20%, 80% will be part of the testing and training in which its performance will be evaluated. 20% will be the validation dataset in which its performance will also be evaluated using the same model that was created in the optimized parameter operator. And then using the same model built on the testing and training and the validation dataset, we're going to apply the same model so that the dependent attribute y will be predicted. And in this process, no performance will be measured since the actual value y is not present. Now we may now click the play button. Now let's compare the result of the performance of the training and testing dataset under performance vector and the performance of the validation dataset which is under the performance vector 2. This shows that our data using the decision tree model is 62.74% using the training and testing dataset, again which is 80% of our data, while the performance of the validation dataset, which is 20% of the data, is 63.13%. So this shows a good result because the performance of the validation dataset is better than the performance of the training and testing dataset. Remember that the higher the value of the accuracy, the better the result is. Now, given this confusion matrix here, the accuracy, which is 63.13%, is computed using this equation given this 2x2 table. Accuracy is computed as A plus D over the total times 100%. However, in this case, this will serve as our A, this will serve as our B, this will be our C, and this will be our D. So 63.13% is computed as 1, which is A, plus D, which is 136, over the total, which is 1 plus 80 plus 0 plus 136 times 100%. You'll have this result. Next, as for the sensitivity, the performance of the training and testing dataset is 0%, while the performance of the validation dataset is 1.23%. This again shows that the performance of the validation dataset is better as compared to the performance of the training and testing dataset. Now, sensitivity in this case is computed using this equation, A over A plus B times 100%. So since in this confusion matrix, this is our A and this is our B, this is computed as 1, which is A, over A plus B, which is 1 plus 80. Again, times 100%. This is the percentage of those correctly identified of having a positive outcome among those with the positive outcome, in which in this case, whether the customer bought the product or not. Next, we have the specificity, in which this result shows that the performance of the training and testing dataset is 100% and the performance of the validation dataset is 100% as well. In this case, the performance of the training and testing dataset and the performance of the validation dataset are the same. And this 100% is computed as D over C plus D times 100%. And given that this is the value of C and this is the value of D, then this is computed as 136 all over 0 plus 136 times 100%. Regarding the true positive, which is just a count, the true positive is just the value of A. In this case, this is our A. So in this case, we have 1 for the performance of the validation dataset and 0 for the performance of the training and testing dataset. So here we see that, again, the performance of the validation dataset is better as compared to the performance of the training and testing dataset. And for the true negative, which is the value of D, in this case, this is the value of D, we have 136 for the performance of the validation dataset and 272 for the performance of the training and testing dataset. Now notice here, although this is not 272, which is the value of D, what the RapidMiner did is that the true negative count was divided by 2 since the minimum folds by default is 2. So using the true negative as a measure of performance, in this case, the performance of the training and testing dataset is better than the performance of the validation dataset. For the precision, which is the positive predictive value, which is computed as A over A plus C times 100%. So in this case, this is your A and this is your C. So this is computed as 1 over A plus C, which is 1 plus 0 times 100%. So given this result, the performance of the validation dataset is better than the performance of the training and testing dataset. So among the criteria, which are accuracy, sensitivity, specificity, true positive, true negative, and precision, which is the positive predictive value, it's only in the true negative where the performance of the training and testing dataset shows better than the performance of the validation dataset, and in terms of specificity, they have the same performance. The rest of the 4 criteria shows that the performance of the validation dataset is better than the performance of the training and testing dataset, which is a good result. Now moving on with the measures of errors, let's have first the classification error, in which classification error is measured as B plus C over the total. So given that this is A, this is B, this is C, and this is D, this is computed as B, which is 80, plus C, which is 0, over the total, which is 1 plus 80 plus 0 plus 136. Since 36.87 is less than 37.26%, this shows that the performance of the validation dataset is better as compared to the performance of the training and testing dataset. Again, classification error is a measure of error, thus the lower the value, the better. Similarly, we have the false positive, in which that is just the value of C. So in this case, this is the value of C. We have 0 here and 0 here. So in terms of the false positive as the criterion, the performance of the validation dataset is just the same as the performance of the training and testing dataset. Last, we have the false negative, which is simply the value of B. In this case, this is our value of B. So 80 for the performance of the validation dataset and 161.5 as the performance of the training and testing dataset. Again, this was divided by 2 to get this one since the number of folds we had by default is 2. Now, since false negative is a measure of error, again, the lower the better, this shows that the performance of the validation dataset is better than the performance of the training and testing dataset. So this shows that based on the 3 measures of errors, for the classification error and the false negative, the performance of the validation dataset is better than the performance of the training and testing dataset. In terms of the false positive as the criterion, the 2 datasets showed the same performance. Now, to summarize the performance of the validation dataset using the decision tree algorithm, these are the measures of accuracy and these are the measures of error. Now, this will be compared using other algorithms or other models such as logistic regression, random forest, naive Bayes, and support vector machine. So all you have to do is to change the model in the cross-validation sub-process, change that to logistic regression, to random forest, to naive Bayes, and to support vector machine, and measure its performance using this criteria. Again, these are the measures of accuracy, which indicates that the higher the better, while these are the measures of error in which the lower the values, the better. All you have to do is to compare it with the performance vector 2 or the performance of the validation dataset. In behalf of the other faculty members teaching this course, thank you for listening.